This is Dr. D. Govardhan, Professor in EDU, Department of Aeronautical Engineering, Institute of Aeronautical Engineering, Hyderabad. Today the topic is the definition terminologies in module number 4, the particles dynamics and work energy principle. Some of the important terms used in kinematics are the speed. The speed may be defined as the rate of change of distance with respect to its surroundings. The speed of the body is irrespective of its directions, hence it is treated as a scalar quantity. Velocity. Velocity of a body may be defined as the rate of change of displacement with respect to its surroundings. It is having some particular directions, hence it can be represented both in magnitude and directions, hence it is known as vector quantity. Accelerations. The acceleration of a body may be defined as the rate of change of velocity. If it is a positive, the velocity of a body increases with the time, and negative if it is a decreases with the time. The negative acceleration is generally called retardations. The distance traveled, it is the distance moved by the body. So mathematically, if the body is moving with uniform velocity v, then in t seconds the distance covered is the product of velocity and time. Equation of a motion in straight lines under uniform accelerations. Let p be the position of the body after t seconds, and u is the representing initial velocity, v is representing final velocity. T means the time required to change its velocity from u to v. This is the distance travelled in t seconds. So the equation for the final velocity is obtained by using v is equal to u plus EAT now. Similarly, the equation of motion for distance covered, it can be obtained by using the relations s is equal to ut plus 1 by 2 at square. The derivations which give the relationship between the final velocity, initial velocity, distance travelled and uniform acceleration is given by v square minus u square is equal to 2as. The distance travelled in nth second is given by u plus a by 2 into 2n minus 1, where n is representing nth seconds now, a is the uniform accelerations, u is representing initial velocity of the body. So the velocity as well as the displacement of a body moving in straight lines can be determined by the integration method. According to the integration method, the velocity at any instant is given by the differentiation of distance with respect to the time now. ds by dt, or ds is equal to v into d, or s is equal to, we can take it as integration of v into d plus c1 is a integration constant. So if you know the velocity as well as the time, the distance can be determined by using integration method. Similarly, acceleration is equal to dv by dt, that is differentiation of velocity with respect to the time, or v is equal to integration of, it can be written as dv is equal to a into dt, or v is equal to integration of a into dt plus c2, where c1 and c2 are the integration constant that can be evaluated by using end conditions. Equation of a motion of a body under the influence of gravity. When the body is moving in downward directions, A is treated as positive. That is the acceleration due to gravity, G is treated as positive. When the body is moving upward directions, the acceleration due to gravity, that is G value is taken as a negative now. So the relations between final velocity, initial velocity and time is given by V is equal to V plus GT when the body is moving in downward directions. The distance traveled, generally it is called moving in downward directions. That is the distance, vertical height that is traveled H, ut plus 1 by 2 gt square. And the relations between initial velocity, final velocity and the distance traveled is equal to v square minus u square is equal to 2a. But when the object is moving in upward directions, the g is replaced with the negative values now, minus g. That is final velocity is equal to v minus u minus gt. S is equal to ut minus 1 by 2 gt square. And v square minus v square is equal to minus 2gh now. Okay, in this case, when the body is starting from the rest, that means the initial velocity of the body is treated as 0, that is u is equal to 0. When the body is coming to the rest, after some times, that is the final velocity is equal to 0, hence v is equal to 0. If the body is projected vertically upwards, the final velocity of the body at which it reaches highest point is 0, that is the highest point v is equal to 0. The body starts moving vertically downward directions, the initial velocity is treated as 0. The acceleration due to gravity is taken as positive when the body is moving vertically downward directions and negative when the body is moving upwards. Okay, the equations are only applicable when the body is moving in linear directions now. But sometimes the body also moves in a plane, curvy, linear motions. Example, the rotation of the shafts, flywheels, pulleys, etc. They rotate about their geometrical axis now. So in this case, the angular velocity of the body, it can be defined as the rate of change of angular displacement. If theta is representing angular displacement of the body in time t seconds, then angular velocity is given by omega is equal to dt divided by d theta. Angular acceleration is equal to, it is the rate of change of angular velocity. Generally, it is measured in terms of radians per second. Mathematically, it can be written as a radian per second square. So, rate of change of angular velocity d omega by dt, which is equal to dt square theta divided by dt square now. The relation between linear acceleration and angular acceleration is given by linear acceleration is equal to rate of change of velocity dv by theta, which is equal to, we got r into d omega divided by d theta, that is we can written as a is equal to r into again alpha now, where a means the acceleration of the linear acceleration of the body, alpha is the angular accelerations. The relation is nothing but here the alpha is multiplied by the radius of the curvature, it gives the linear velocity, linear acceleration. Equation of a motion of a body along the circular path. Let omega naught is representing initial velocity of the body in radians per second. Omega represents final velocity of the body. T is the time t in seconds taken to reach from initial velocity to omega naught to final velocity to omega. Theta is representing angular displacement in radians. Alpha is representing angular acceleration of the body expressed in radians per second square. Then the relations between initial velocity and final velocity is given by, that is omega is equal to omega naught plus alpha t naught. Similarly, angular displacement is given by d equal to omega naught t into 1 by 2 alpha t square now. The relationship between initial velocity and final angular velocity, angular accelerations and angular displacement is given by omega square minus omega naught square equal to 2 into alpha into theta now. When the speed is represented in revolutions per minute, that's RPM, then angular velocity is given by 2 pi n by 60. Dynamometers principle for kinetic problems. Here we are considering an object. It is subjected to F1, F2, F3 and F4 forces. Because of all the forces, the body is assumed to moving in the direction of X as shown in figure. Or in other words, the resultant of F1, F2, F3, F4 is equal to R now. The direction of R is in the direction of motion the object is moving now. So simply just it can be represented as R is equal to M into A now, where R stands for the resultant of F1, F2, F3 and F4. M is the mass of the body. A is the acceleration with which the body is moving in the direction of X. So this equation can be modified as R minus MA is equal to 0 now. That means the Dynamometers principle states that when the system of forces acting in a body, when it is in motions, is in dynamic equilibrium with the inertia force. That is system of forces. Here F1, F2, F3, F4 are representing the system of forces that are acting on a body. Here it is a moving now. That is R is equal to M into A now. It can be written as R minus MA is equal to 0. Where M minus MA is treated as the inertia force now. That is when the body is in motions, when the system of forces are acting on the body, it always keeps in dynamic equilibrium with the inertia force. This principle is known as Dynamometers principle. Where M is equal to mass of the body, A is representing the acceleration with which the body is moving now. Since the body is moving, the R minus MA is now treated as dynamic equilibrium. This principle is known as Dynamometers principle. Just it is having applications in solving problems in engineering fields such as motion of a lift, when the bodies are connected by a string and moving over a frictionless pulley, when the bodies are moving on inclined planes and connected bodies moving in horizontal planes, all these problems, almost all the problems that can be solved by using Dynamometers principle, in which force as well as the acceleration are involved. Here consider lift now, motion lift. Let M is representing the mass carried by the lift. A is the uniform acceleration of the lift. R is equal to reaction of the lift, R tension in the cable. Here we are taking, it is now lift, it is there, that mass. Now it is attached with the string. Assume here R, T the reactions now. It is given now. W is the weight that is acting in normal directions. Okay, we can solve the problems for determining unknown forces by using just two methods now, two categories. When the body is, when the lift is moving downward directions and when the lift is moving upward directions. Here when the lift is moving downward directions now, I told this is nothing but representing the lift. Just having mass is equal to M is given now. T is nothing, R is nothing but tension in the rope. Here first case is the R1. The weight W is acting in downward directions. Since the lift is moving in downward directions now, that inertia force is always acts in which the body is accelerating. Because the body is accelerating in downward directions means the inertia force is equal to minus MA. Minus is nothing but representing here it is in upward directions in which the acceleration is acting now. That is, you have to represent in upward directions. Direction of inertia force is since the body is accelerating downward directions, inertia force is acting upward directions now. So here now three forces are involving. One is the tension in the rope. The second one is the weight of the body in downward directions. Inertia force is always acts in opposite directions in which the body is accelerating. So under these three forces, the body is in dynamic equilibrium according to the D'Alembert's principle. Hence, here while taking equilibrium position, the forces which are acting in upward directions are treated as positive, and the forces which are acting in downward direction are treated as negative for calculation point of view. Hence, R1 is a positive, inertia force is a positive, and weight of the body is treated as a negative values now. So, R1 plus W by G into A minus W is equal to 0. From this relations, we can take R1 is equal to W minus WG by G. That is the tension in the string, it is obtained by using this relations. Similarly, when the lift is moving upward directions now, the forces which are acting on the lifter, the weight is acting in downward directions now. Assume R2 is representing the tension in the string. Since the body is accelerating in upward directions, hence the inertia force is always acts in opposite directions in which the body is accelerating. That is, according to this problem, it is in downward directions. And applying D'Alembert's principle, that is equal to R2, that is positive because it is upward directions now, and inertia force acting downward directions, so minus of W by G into A. The weight is also acting downward direction, so it is negative. It should be equilibrium now. This is called dynamic equilibrium because the body is moving, but the resultant force acting on the body is equal to 0. Or in other words, when the system of forces are acting the body, it is always the body is in equilibrium with the inertia force now. So by using this relationship, we can determine the reactions within the string. Similarly, the motion of a body on inclined plane. Here the body is resting on inclined plane now, where alpha is representing inclination of the plane with the horizontal. Let first we are considering alpha is less than the limiting angle of friction now, less. Hence, in order to move the body up the plane or down the plane, some external forces is required. In case 2, when alpha is greater than limiting angle of friction, that means when the body is kept over the inclined plane, automatically it tends to slide downward direction, even though there is no forces are acting on it. In that case, in order to keep the body equilibrium positions, that is preventing its motion downward directions, some external forces required to keep it in equilibrium. At the same time, in order to move the body in upward direction also, some forces are required now. Okay, in this case, we are considering the inclination of the plane is more than the limiting angle of friction. Okay, here we are considering here 3 types depending on type of the forces that are acting on the body. When the body tends to move in downward directions as well as in upward directions. Here in case 1, the body is moving in upward directions when the applied force is parallel to the inclined plane as shown in figure. That it is moving in upward directions. So let us consider alpha is representing inclination of the plane, W is representing weight of the body, P1 is the force that is applied to move the body up the plane. Now drawing just a free body diagram now for this one now. The weight is acting here downward directions, W. Resolve these forces into components, one is along the plane and perpendicular plane. So after representing the here perpendicular and horizontal now, that is the weight is acting perpendicular downward directions and horizontal component is acting in downward directions as shown in figure. Now P the force that is applied along the plane P1. The friction force which is experienced between the body and the contact surface F1 is equal to mu N1. It always acts in opposite direction into the body tends to move or the moving. Here the body tends to move in upward direction since the frictional force are taken in downward directions. So inertia force is there now. The inertia force is always acts in opposite directions in which the body tends to accelerate. Since the body is moving upward directions, the inertia force is acting downward directions. Now keeping all the forces in dynamic equilibrium, that is the resultant force should be equal to 0. Or in other words, when the system of forces acting on the body, when the body is in motion, always it is in equilibrium condition with the inertia force now. Hence, by using this relationship, we can determine what is the minimum force P1 that is required to move the body up the plane now. Similarly, when the body tends to move in downward directions now, that is the frictional force is acting upward directions now. Inertia force is also acting upward directions. The weight component is that is a vertical component in downward directions and horizontal component toward the left hand side. Here P is nothing but the force that is applied the body. Again we can solve these problems by applying Dynamometers principle to get the minimum force P2 required to move the body in downward directions. In third case, the applied force is parallel to the ground now, that is in horizontal directions now. But the body is moving up the plane as shown in figure. In this case, the forces are resolved along the plane as well as the perpendicular plane. Here the weight is resolved into two components as usual like previous one. The horizontal force P is resolved into two components now. P sin alpha and P cos alpha. And F is the frictional force. Since the body is moving in upward direction, so the resultant, that is the inertia force, acts in opposite direction in which the body tends to accelerate, that is in downward directions. Again, by applying equilibrium condition, we can determine what is the minimum force P required to move the body up the plane. Here the applied force is making an inclination of alpha, this in downward directions, horizontal now. When the applied force is making inclination theta with the plane surface, again in that case also the P is resolved into two components now, P sin theta and P cos theta. W again two components, W cos theta, W sin theta. Since the body tends to move according to the problems in downward directions, inertia force acts upward directions. So applying again Dynamometers principle, that is the sum of the system of forces, the resultant of system of forces with the inertia force that should be in equilibrium, that is the resultant of all the forces must be equal to 0. We can determine what is the value of P that is required to move the body up the plane. Here for this one down the plane. Okay, Dynamometers principle for the connected bodies. Here the two bodies are there now, W1 and W2. They are connected together by using the inextensible string as shown in figure. Both are lying on rough horizontal plane. Let P be the force applied toward the left side of W1 as shown in figure to move the system of bodies W1 and W2 toward the right hand side. Let T be the representing tension in the string now. Okay, in order to solve the problems, that is for the minimum force P required to move the body towards the right side, as well as the tension developed within the string can be determined by using Dynamometers principle. Okay, in these problems, first of all, analyze the forces for the block 1, after that block 2. This totally we are getting just 4 equations now. By using these 4 equations, we can determine the values of P as well as the T now. Here I am taking now W is equal to weight of the first block W1. Assume this is nothing but representing W1. T is the tension in the string. The tension is always acts away from the object as shown in figure now. P is the applied force is there. Since the body is moving toward the right hand side, and inertia force is always acts in opposite direction which the body is accelerating. So inertia force is equal to W1 by M into A, W1 by G into A. It is acting toward the left hand side now. So friction force is always acts in opposite direction which the body tends to move or moving. So it is also toward the left hand side. That is F is there now. It is acting up. N is there. The normal reaction is acting upward direction. So it is compensated with the weight of the body. So F is equal to W1. By using the relationship, we can determine the what is the N is equal to W1. By using the relationship, we can determine the values of F now. So integrating that is taking this resultant of all the forces now. In this equation, we got the forces which are acting toward the right hand side as positive, left hand side negative. That is P positive, we have taken now. T negative, and friction force is also negative, and inertia force is also negative. So it should be equal to 0. From this relationship, we can determine what is the value of T. Here, according to the problems, T and P are unknown quantities. Hence, we are taking just one more object now. That is W2 now. That is weight. Here the body tends to move toward the right hand side only. Here tension is away from the object now. Weight is equal to W2. Inertia force is equal to W2 by G into A, because it is moving toward the right hand side. Hence inertia force is acting toward the left side now. Ft is the frictional force. It is acting toward the left side. Nt is the normal reactions of upward directions, and W2 is the negative directions now. Okay, from this relation we got N2 is equal to W2, or F is equal to mu into F. That means mu into W2 now. Applying Dynamometers principle for this body, we got the forces which are acting toward the right hand side as positive, left hand side as negative. Answer T positive. Here frictional force negative, inertia force also negative. It is equal to 0. By using the relationship, we can get the values of T now. So substitute the values of T, we can determine the value of P, that is the minimum force that is required to move the body toward the right hand side now. Similarly, the Dynamometers principle can also apply for the pulleys also. Here the two bodies are there, W1 and W2, they are moving connected together by the string and passed over the pulley as shown in figure. We can determine the velocity with which the body is moving or tension in the strings by applying Dynamometers principle. Here another application is, here one object is lies on horizontal plane now. One more object is hanged vertically downward directions. by using inextensible spring which is passing through over friction pulley as shown in figure. The velocity with which the body is moving downward directions or tension in the string can be determined by applying D'Alembert's principle. Similarly, the object is moving along the inclined plane due to weight W1 that is angled in vertically downward directions by using the string which is connected together and passing through over a frictionless pulley. The tension as well as the speed at which the body is moving can be determined by using D'Alembert's principle. Okay, these are the various applications of the D'Alembert's principle. Generally, when forces as well as the accelerations involving, then this problem is, this principle is easy for the analysis of forces which are acting on the body. Work. When a force is acting on a body, if the body undergoes certain displacement, then the work is said to be done on it. Okay, work done is equal to, generally it is represented by capital letters W. It is equal to force into distance, that means product of force applied and the distance moved now. That is P into S now. Here generally P is represented in newtons, the distance in meters now. The work done is equal to, it can be written in Newton meter, the value which is equal to 1 joule now. In case 2, if the applied force is making an inclination of P, that is with the horizontal as shown in figure, here the two components of force are there, vertical and horizontal now. This vertical force is not at all contributing any work done on it, because the body is moving in horizontal direction, means we have to take the component of force which is acting in the direction of motions, that is P cos theta. That is the work done is equal to the component of force which is acting in the direction of motion, so multiplied by the distance moved, which is equal to P cos theta into S now. Power. Power is defined as the rate of doing the work. Generally, it is used to measure the performance of the engine now. Okay, work done by nothing but power is equal to work done by, here we are taking time now. It is equal to, work done is equal to, already we have taken force into distance divided by time now. Force is generally expressed in newtons, distance traveled in meters, divided by time in seconds now. Newton meters is nothing but joules per second. Joules per second, it is treated as watt. Okay, types of engine powers. The engine powers are generally measured in terms of indicated power and brake power. The indicated power is the actual power generated in the engine is called indicated power, and the brake power is the net power that is available at the shaft for running the machines is called brake power. Here the brake power is always less than indicated power because of some friction losses that are taking place due to the presence of so many moving parts. Hence, the efficiency of the engine is defined as the brake, it is the ratio of brake power divided by indicated power. Generally, it is expressed in terms of percentage, that means multiplied by the 100 now. The brake power can be determined by using the apparatus that are called dynamometers. These are classified into absorption type and transmission type. Energy. The energy may be defined as the capacity to do the work. It exists in many forms like mechanical, electrical, chemical, heat, light, and etc. Since we are taking the energy is the capacity to do the work, hence the work as well as the energy both are having the same units. The unit of energy as well as the unit of work that are represented in the same, that is Newton meter, which is equal to 1 joule now. But here we are concentrating more on mechanical energies only. These mechanical energies are classified into two types now. They are important two types. One is potential energy, one more is kinetic energy now. The potential energy, it is the energy possessed by the body by virtue of its position only. So consider mass m raised through height h from the ground level. Then the potential energy possessed by the body is equal to the weight into distance moved in upward direction. That is mg into h now, or mgh. This is called potential energy because the energy stored within the object by virtue of its position only. And the kinetic energy. The kinetic energy possessed by the body is due to the virtue of its mass as well as the velocity of the body. That is here kinetic energy is equal to, we can take it as 1 by 2 into mv square now. That is, it is the energy possessed by the body by virtue of its mass as well as the velocity with which the body is moving now. So the equation for determination of kinetic energy is given by kinetic energy is equal to 1 by 2 into m v square. But sometimes the change in velocity, change in kinetic energy is given by 1 by 2 into m into v square minus v square, where v stand for the final velocity of the body, u stand for the initial velocity. This equation is used to determine the change in kinetic energy of the body when the velocity changes from u to v now. Okay, here now we are taking one object now. System of forces F1, F2, F3 and F4 are acting on a body. Because of all the forces, the body is moving in the direction of x as shown in figure. Let S is representing the distance traveled by the body in t seconds now. Let the initial velocity at a point A is given by u. After time t, when it reaches the point B, the final velocity is v. The distance traveled is equal to s now. And a be the acceleration of the body. The resultant of all the forces in the direction of x when it is resolved, assume r is the resultant of all the forces in the direction of x now. Then r is equal to, that is resultant of all the components, all the forces is equal to, which is equal to m into a, because m is the representative mass of the body, a is the acceleration which the body is moving on. But m is replaced by w by g into a, or w by g into dv by dt now. So work done is equal to m into dv by dt, which is also equal to, we can written as ds by dt into dv now, or m into v into dv now. So r into a is equal to, we can take it as now integration from 0 to s into ds is equal to m into integration of u to v into VdV. R into S is equal to, because the distance traveled is equal to S, which is equal to M into, just V integration is V square by 2, but limits are just, we have to do the integration from U to V and so on. So R into S is equal to 1 by 2 M into V square minus V square. Or in other words, R into S is representing work done. The work done is equal to change in kinetic energy of the body. Okay, work done by virtue of its mass and velocity of the motions. Here the spring we are taking now. Spring is a common tool. When you stay in, will undergo some displacement due to compression. Then it comes to equilibrium positions when the forces are released now. So the spring exerts an equal as well as an opposite force on the body that compresses or stretches because of its potential energy. Okay, the work done in stretching the thing from initial position 0 to a displacement of x is given by work done is equal to 0 into x into f into dx. Or it is equal to, we can write as work done is equal to, that is work done for compressing the spring is given by equal to 1 by 2 into kx square with a negative sign, because the spring force which is acting on the body is the opposite direction of its displacement, where x is representing the displacement of the spring. That is the work done on the spring is given by minus half 1 by 2 kx square now. So since the energy is stored within the object now, potential energy, it is used to do the work later, because the energy is treated as a capacity to do the work now. Okay, depending on the stiffness required, the springs are connected in series as well as the parallel now. So the spring force is given by F is equal to K into X, where K is representing that is equivalent to stiff constants when the springs are connected in series or in parallel. Okay, thank you. These are the important terms, D'Alembert's principle as well as the work done.
Like, share and subscribe. Hit the bell icon for more updates.